Hello, everyone, and welcome to this session of Multiple Universes. I'm James Barbieri, Associate Program Director of the Power Center, and I will be your host for today. And as a host, if you've got any problems, technical or not, just feel free to drop me a message in the chat. Before I begin, I'd just like to go over very quickly the Zoom rules for this call. First of all, if you could please mute your microphone during the presentation and Q&A, just to ensure good quality audio. But at the same time, please, we do encourage you all to turn on your cameras, as at least we're not talking to just a blank screen. During Q&A and discussion, if you want to make a contribution or ask a question, use the raise your hand function, physically raise your hand, or write your question in the chat, and I can read that out for you. And finally, this session is recorded for archival purposes and for you all. The recording will be uploaded about 3 days after this session to Vimeo, so you should all receive the link to that. Okay, so now we can start. Today we have the honor of introducing Tim Maudlin. Tim is a professor of philosophy at NYU and founding director of the John Bell Institute for the Foundations of Physics. His research revolves mainly in the foundations of physics, metaphysics, and logic, topics of which he's written several books on this. Today, Tim will be talking about science, philosophy, evidence, explanation, and fine-tuning. So with that, I'll pass it over to you, Tim. Welcome.
Thank you. So let me explain, first of all, how this particular talk came about. When I was originally invited, I had planned to do a talk that basically Bernard Carr already gave you, at least 90% of it. I was just going to kind of overview the different sorts of multiverses, and so I didn't, after hearing his talk, I didn't see any point in plowing the same ground again. And something else happened, which was that there was a kind of not really explicit but tacit set of assumptions that I think were underlying some of the comments that were made that I thought really deserved to be discussed more straightforwardly. And so I prepared the presentation that I'm going to give you. So it's a bit in reaction to some of the things that happened there, and it's focused very much on fine-tuning in the end, although there are more important general points to be made before that. I'm not sure how long that will take. I hope it won't take very long, and that it'll be somewhat provocative and people will want to talk. In case it isn't provocative or nobody wants to talk, I also prepared a second very short little presentation about many worlds, which is not something that's going to be the focus of these first comments. And if there's extra time, I can go through that. That's just more technical about what the situation is with respect to what you'd have to do to make sense of the many worlds interpretation. But I'll make some comments about why the Everett interpretation isn't really relevant for what I'm going to be talking about today. So let me get this started. And there. Okay. Everything good? Good. So you can see there are a lot of topics here, but they're all interconnected and they'll go by pretty quickly. So I want to start by just raising some questions that, again, have been discussed at least in passing or mentioned at least in passing already in the conference, particularly, as I say, in Bernard's talk. So the question is there a strict line or distinction to be made between the following pairs of things? Science and philosophy. Can we draw a strict line there? Physics, in particular, obviously, and philosophy. Physics and something called ontology, and physics and metaphysics. And, especially the last one, I guess, part of this was brought about by people saying, oh, we've left physics and now we're doing metaphysics and things like that. So let me just at least provide my answers to this. And note, I'm talking, is there really a kind of really determinate strict line? The answers, I think, are no, no, hell no, because, and let me just say a word about that, because ontology, it's not a typical word used outside of philosophy, but all it means is an account of what exists, right? Ta onta in Greek are the things that are. And particularly at the kind of most general generic level, when you're discussing what exists, then you're doing ontology. And one sure hopes that physics will have very forefronted within it such a discussion about what exists, about what there is. And then, well, what about physics and metaphysics? And it's very easy to say, there must be a distinction. But in fact, all right, there we go. In fact, the word ontology and the word metaphysics are synonymous. So if there's no distinction between physics and ontology, there's no distinction between physics and metaphysics either. I mean, I could go into the history. Metaphysics is a funny word because it was attached to a bunch of writings by Aristotle which don't contain it. So it was not a word that he ever used. But I mean, shortly, what he thought he was doing was giving an account of what he would say of being qua being, as we say, or being as such, or what exists discussed at the most high level of abstract generality. And in fact, it's a bit interesting that John Bell, who will come into this discussion, kind of invented the word beable, which he just made up. And it's the English version of ontology, because just as ta'onta comes from what is, he's using be, right? Being, what the beers he thought he might use. And he just meant things that are postulated to actually exist. So I don't think that you could draw any sharp line. And the question, one question is whether you can even draw any useful line between these topics. Now, I'm going to give a very quick and, as I say, directed argument, because it has certainly been at least presupposed in some of the comments that there is a division to be made here, and gee, we've wandered from physics to metaphysics or something like that. So let me just give a very quick directed argument directed at a physicist who wants to claim there is a strict division between physics and philosophy. So the directed argument goes like this. I want to start by asking, if there is such a line, on which side of that line does the question, is there a strict line to be drawn between physics and philosophy, lie? Okay, if you want to insist there's such a line, tell me on which side this particular question goes. And I think the answer has to be, it doesn't go on the physics side, because you certainly, at least you don't decide it by experiment, or you don't decide it by any of the standard techniques of physics, right? So if you want to insist there's a strict line, you're going to also, I think, have to concede it's on the philosophy side of the line. So according to you, the question should be settled, right? According to you, physicist who thinks this question ought to be settled by philosophers. But philosophers, including me, say there is no such line. So you're in a bit of a sticky situation here, right? If, as a physicist, you want to insist on this distinction. But I need to say something more. It's a very particularized argument at very particular people. I want to give a just more general answer. And in order to give that, we have to start with the question, basic question, what is physics anyway? And I want to give a shot, as I say, I could go on much more than you'd be interested in about this, but I think this is okay, at least for what we would call fundamental physics. It's maybe not good for other parts of physics that wouldn't be generally considered fundamental. But that physics provides as a generic account at the most fundamental level of entities, structures, and laws that give rise to the motion of matter. I mean, the idea that ultimately physics is the scientific study of matter in motion goes back a long way, and it's not, I think it's pretty good. Now, having said that, there are various things you now need to make more clear about it. But here are just some examples of what I mean. So I say in account of the entities, structures, and laws. So what would you mean by an entity described at this most generic level that would be postulated by physics? Well, democracy and atoms, right? So we go all the way back to the pre-Socratics, and they were doing this. They were called often nature philosophers. What they were doing was certainly the beginnings of physics and the beginnings of philosophy by anybody's account. So, you know, Democritus put forward a postulate about fundamentally what matter is made of. Boltzmann certainly also held an atomic theory. There's no reason to think, and every reason not to think, that he conceived of his atoms the way Democritus conceived of his. Then we get to electrons, protons, funny new things like electromagnetic fields, quarks, strings. And the last thing on the list, I have what I'll call quantum states, which is foundational to any understanding of quantum mechanics, but whether you want to call a quantum state an entity is why I've put the question mark there. What do I mean by structures as opposed to entities? And again, you not necessarily draw a strict line here. Newtonian space and time are a kind of structure. I mean, certainly they have a geometrical structure. A thing called neo-Newtonian space-time, which has a slightly different structure than Newton postulated. Minkowski space-time, the space-time of special relativity. Four-dimensional space-time of variable curvature with a Lorentzian metric, which is basically what you have in general relativity. 11-dimensional space-time postulated by string theory. And again, someone might say, well, really, these quantum states, maybe they should go there. Maybe they're not really entities, but they're more like structures. What about laws? Well, Newton's laws of motion, Maxwell's equations, general relativistic field equation, Schrodinger's equation. And again, it has been suggested in very specific circumstances for very specific reasons. Maybe the way to think about quantum states are that they're more like laws than they are like entities or structures. And we could have a long discussion about that. But the quantum part, it's not quite clear where this new item that's postulated by quantum mechanics goes, and there's been a lot of discussion about that. But it's certainly regarded as a fundamental feature of the physical world, and so part of fundamental physics. Now, there's a second question that comes up. So this is just if physics is what I just said it is doing ontology, because part of it is postulating the existence of entities, of structures, of laws. The second and really quite orthogonal question, different question from this, is going to be why one should ever take seriously or believe any of these proposals, right? On what grounds should one think, yeah, maybe that's right? And of course, whenever you raise that question in fundamental physics, there's the history of physics to warn you that stuff that people very strongly believed in has turned out not to exist, right? There is no luminiferous ether. Democritus was wrong about his atoms. It looks like Newton was wrong about his fundamental equations of motion and theory of gravity and so on. So you ought to be a bit cautious about taking these things seriously and think a little bit about what it even means to take it seriously, at least seriously enough to do further research into them. So one of the things that obviously the basis for taking some of these proposals seriously is what we would call experimental evidence. Another thing which you do want to distinguish is what I would call observational evidence, but not particularly produced by experiments. The return of Halley's Comet that was predicted after Newton proposed his theory was taken as very strong evidence that his theory was correct, or at least on the right track. That wasn't an experiment, right? They didn't set that thing up. all of the evidence for evolution that you get out of the fossil record is not being produced by experiment. It's being produced by digging around and crossing your fingers and hoping you find something that would have significant evidential bearing on the questions you're interested in. There are implications from accepted principles. So sometimes you come to believe that things exist, not because you've observed them, but because you've, for other reasons, accepted a theory that imply that they exist. And an example here is neutrinos. They were originally postulated because it looked like, from all the observed things you could see in an interaction, that the laws of conservation of energy momentum would be violated, right? So you could watch the tracks after a certain kind of decay and say, gee, from what I can see, energy, both energy and momentum, has gone missing. And so originally the thought was, well, if I believe in the conservation of momentum and the conservation of energy, that must have gone somewhere, and it must have gone into some particle that is not showing up in my experiment, and that's why they were neutrinos. They couldn't be electrically charged. But that was not, in any normal sense, direct observational evidence. It was inference from a theory that you thought you had good reason to believe. And then there's this other principle, which is fairly widely discussed in the philosophy of science, which goes under the general name inference to the best explanation, where you say, all right, I don't really have direct evidence of this, but if I postulate that this exists, it will account for things that I think need to be accounted for. This happens, of course, all the time in reconstructing evolutionary history, where you think there must have been intermediate evolutionary forms that just haven't shown up in the fossil record, and maybe they never will. You know, fossils are formed by luck, and many species, and many more, most individuals will never fossilize, and most fossils will never be recovered. But nonetheless, you can think, gee, we really have good reason to believe there were various sorts of intermediate biological forms that connect up parts of the fossil record that we have. So these are the range of considerations that could make it reasonable to take a proposal seriously is pretty wide, and one needs to keep an eye on it, especially if you're dealing with a question like multiverses, because as should already be obvious, you're of necessity typically getting away from direct observational evidence. Now, in terms, I just wanted to bring up this quote. I have several quotes from John Bell, because there is this idea that no, physics or science is based on experiment, right, on experimental evidence. And Bell said something very nice about it. And so this is just a quote, right? So he says, this is in the paper Against Measurement. Even in a lowbrow practical account, I think it would be good to replace the word measurement, and I'm sorry if I'm getting the words wrong because I can't see the right-hand side of this. Replace the word measurement in the formulation with experiment, for the latter word is altogether less misleading. However, the idea that quantum mechanics, our most fundamental physical theory, and you'll notice again, fundamental comes up just spontaneously in this discussion, is exclusively about the outcomes of experiments, would be, I'm sorry, I can't read that word, disappointing. In the beginning, natural philosophers tried to understand the world around them. In doing that, they hit upon the great idea of contriving artificially simple situations in which the number of factors involved is reduced to a minimum, divide and conquer. And this is exactly right. I mean, what was great that Galileo did was he contrived experimental situations where particular facts about how things fell, or making them, as it were, fall more slowly by having them roll down inclined planes, made things measurable and checkable in various ways. They wouldn't be if you just opened your eyes and looked around in the world and didn't go to the trouble of designing these things. But experiment is a tool. The aim remains to understand the world. To restrict quantum mechanics to be exclusively about piddling laboratory operations is to betray the great enterprise. A serious formulation would exclude the big world, will not exclude the big world outside the laboratory. So I think that's exactly correct in terms of people who focus too monomaniacally on experiments. And there's a certain kind of so-called operationism sometimes, which very much lends itself to a fairly exclusive focus on experimental situations. Now, suppose you raise this question, the second question, that on what ground and to what extent should we take a proposal seriously? What kind of question is that? In philosophy, that question falls under the general category of epistemology or confirmation theory. And I guess I know enough from having had some part of a physics education, that aside from some technical work in mathematical statistics, this just isn't a question that's particularly discussed in physics classes. You're taught the theory, and you're not taught why you should take the theory seriously. Sometimes examples are used that involve observations and evidence, but typically not from the point of view, gee, let's think about what all other alternatives there might be, or how strong this evidence is, or what it rules out, or what it rules in. They're just kind of advertisements, as it were, for the theory. And once you get into these questions of what constitutes credible evidence, these are difficult, and they're not much, they're not much discussed explicitly in a physics education. Now, if you were to insist on, therefore, if you were to go back again and insist, no, there's just a sharp divide between physics and philosophy, for example, then I think you would have to be stuck by saying that the people who are really experts and have devoted their lives to trying to understand confirmation theory tend to live in philosophy departments. They don't tend to live in physics departments. And then you would have to just concede this question of why should we take any of these theories seriously to the philosophers? And my guess is the physicists aren't particularly going to want to do that. And I think Bell gives you a perfect example, and for reasons I'm about to go into, of a physicist who thought deeply about this and did that as part of doing physics, right? That this is a question that ought to come up within physics proper, namely, why should I take a physical theory seriously? And Einstein wrote very penetrating things about this. And Schrodinger certainly worried a lot about it. And even though I would strongly disagree with what they said, Bohr and Heisenberg and Wheeler all discussed these sorts of issues. So certainly they're part of physics practice. Now, why is it important to hit this question head on, right? Is there really a distinction between philosophy and physics? Is there really a distinction between philosophy and science? And is there a distinction between physics and metaphysics, right? Why should we even care about this? And I think it's because the incorrect answer, namely that these are quite different disciplines and don't have a lot to do with each other directly, that incorrect answer is, I think, first, it's conceptually inaccurate for reasons that I've basically been talking about. It's historically inaccurate for reasons I'm about to go into. But most importantly, it's just counterproductive. It has a tendency to exclude work or denigrate work even that is very important, and maybe not enough of it is being done. So let me just illustrate that. I mean, it's often said that metaphysics, or more particularly the interpretation of quantum mechanics, as it's called, is the sort of thing a serious physicist does on the weekend. I think this there was a comment of this form that got me started thinking about this. Oh yeah, after you've done your serious work during the week, maybe you have a few beers and you kick back if you're a physicist, and then you do this stuff, right? And that's what a real physicist would do, and take it with kind of that level of seriousness. Now, I just want to point out some just plain facts, okay? John Bell was a serious physicist, and he had his everyday, weekday, Monday to Friday work, which, as far as I understand, was designing magnets at CERN. And he did do something on his weekends and on his sabbaticals that was not part of his official job description, which was to do this foundational work. And I think, and I'm not alone in this thought, that he deserved the Nobel Prize in physics, and that he would eventually have gotten it if he hadn't died so young. And then you have to notice that Nobel Prize in physics, if he had gotten it, would have been for his foundational work, right? If he had not done that work and had been a serious physicist doing his everyday, Monday to Friday work designing magnets, I'm sure he did a great job at it, but he would not have gotten any kind of particularly long-lasting recognition for it. Insofar as he did something really ground-shakingly, earth-shatteringly important for physics, it was what he did on the weekend. But that's just I don't think anybody can dispute that. So why was it so important? Well, let's just look at what Bell did. And again, if people don't know any of this, I'm not going to go into the details, but I take it everybody has some idea. I just want to say quickly both what came out of Bell's paper and what went into Bell's paper. What really came out of it, I think people agree, was it inaugurated what's been called the second quantum revolution, the one after the one that started in the 1920s. Directly, violations of Bell's inequality, I believe, prove the existence of a real physical kind of non-locality in the world. So this is I think, perhaps the most astonishing discovery that physics has ever attained. And aside from doing that, it focused attention on states of entanglement that involve distinct systems, what would normally be thought of as distinct systems. And that focus on entanglement and its physical characteristics led to quantum computation, quantum cryptography, quantum information theory, and quantum teleportation. None of those fields would have existed in the way that they do if not for Bell's work. So, one can't say that this wasn't a work of extreme foundational importance for physics, for anything anybody would call physics. Well, what went into the paper, right? Why did Bell end up writing that paper? Well, what set him off, and he says this quite clearly, was reading Bohm's 1952 paper, which was on pilot wave theory. And here's what he has to say about it in his paper on the pilot wave theory, this paper on the impossible pilot wave. But why then had Born not told me about this pilot wave, if only to, sorry, again, I can't read it, say what was wrong with it? Why did von Neumann not consider it? Most extraordinarily, why did people go on producing impossibility proofs after 1952 and as recently as 1958? He wrote that paper in 1958. when even Pauli, Rosenberg, and Heisenberg could produce no more devastating criticism of Bohm's version than to brand it as metaphysical and ideological. There you have the word metaphysical again being wielded as a kind of cudgel against a theory, right? You don't like Bohm's theory, but you can't actually say that it makes any bad predictions. And you can't bring any other real complaint against it. You say, oh, it's metaphysics, and thereby dismiss it, right? Yeah, it is metaphysics. It's an account, it's an attempt to give you a very clear account of what there is in the world. Why is the pilot wave ignored in textbooks? Should it not be taught not as the only way, but as an antidote to the prevailing complacency, to show that vagueness, subjectivity, and indeterminism are not forced on us by experimental facts, but by deliberate theoretical choice? And again, there's nothing, I think anyone who understands the situation is going to agree with everything Bell says here. So Bell reads, he was always kind of puzzled and dissatisfied with quantum theory as it had been presented to him in his classes. And then he reads Bohm's paper, and all of a sudden he says, gee, all this stuff that I've been told is forced on us, right, is required by quantum theory or by the phenomena that gave rise to quantum theory. Here's a theory that will give you all those predictions. It doesn't have any of it. The paper is called On the Einstein-Podolsky-Rosen Paradox. And so that tells you that it came out of Bell, again, thinking hard about what Einstein, Podolsky, and Rosen had written in 1935. And the 1935 paper itself is really just a kind of very sharp formulation of the objection that Einstein had had to quantum theory starting already in 1925 against the spooky action at a distance implicit that he saw was implicit in the Copenhagen approach. Implicit because in the Copenhagen approach, they insisted on the completeness of the wave function. And that paper, the EPR paper, also inspired Schrödinger to write his CAT paper, which I'm convinced very few physicists have read because they don't seem to understand the point of it. And in that paper, it was Schrödinger who understood the importance of entanglement and insisted on it. Later in a different paper that year, he wrote this very nice thing. When two systems of which we know the states by their respective representatives enter into a temporary physical interaction due to known forces between them, and when after a time of mutual influence, the systems separate again, then they can no longer be described in the same way as before, by endowing each of them with a representative of its own. I would not call that one, and this is just a very nice sentence, I would not call that one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. Notice, it's not indeterminism, right? That's not the issue. That could easily be incorporated into what would be broadly understood as a classical picture. And so all of this idea that, oh, the big deal was determinism, that's not right, certainly not right for Schrödinger. And Schrödinger said, what's really weird about this theory and unexpected from a classical point of view is entanglement. And then what Einstein had been insisting on really are the consequences of entanglement among easily seen entanglement among distantly separated systems. Although for Einstein, it was obvious even with a single particle, if you take collapses seriously, there's a kind of non-locality involved. By the interaction of two representatives, the quantum states have become entangled. So what's the conclusion? So first of all, unlike the idea that, oh, worrying about the interpretation of quantum mechanics is not a serious thing that a physicist does. It's some other kind of non-serious thing that a philosopher does. And all of this, you can see how it falls together with this idea that there's a sharp divide between physics and philosophy and so on. Worries about what's normally called the interpretation of the quantum formalism, which is worries about how the world might be, right? What is the world actually like, such that the standard predictions of quantum mechanics are correct, is not a philosophical adjunct to or distraction from real physics. These worries drove Einstein, which then drove Schrodinger, which drove Bohm, which drove Bell, a line of physicists who were sensitive to these problems, and has led to the most important, I would say, result, as I say, is Bell's result, and these are parts of physics as such. And I think after this long prelude that exactly the same thing is true if we worry about many worlds or many universes. This isn't, you can't just wave your hand at it and say, oh, that's metaphysics, or oh, that's philosophy. It's not, it's physics. These are physical proposals. And you have to think, on what grounds might we take them seriously? Now, for that, I just thought I'd again go through just some examples of other cases in the history of science where it turned out there turned out to be a whole lot more X's for some given X than we were aware of, and the grounds upon which we came to accept that. And that's happened kind of over and over again, if you think about it, in the history of science, that something that was originally thought to be scarce or maybe unique turned out actually there are lots of them. We could ascribe to Galileo, I don't, the history here is not entirely clear to me who to ascribe this to, but that there are many, many, many objects that are akin to the sun. I mean, everybody knew there were lots of stars, but it wasn't at all obvious that this many stars you see at night were objects whose nature was in any way similar to the sun. You have the proposal, again, we could put this down to Giordano Bruno, who certainly made it, and people before him, that gee, maybe there are many planets in some way like the Earth, and that the Earth is not at all unique in a way that a geocentric picture of the universe would absolutely demand. And we all know Bruno got into some difficulties over that particular proposal. Certainly the discovery that there have been many, many more species than had been assumed to exist before Darwin and work that came after Darwin, and the existence of those many, many species, most of whom died out, is central to the viability of the theory of evolution. So once again, you have a postulate that there are a lot more X's than you thought there were. And that postulate turns out to be absolutely central to the scientific viability of a certain explanation. It has been postulated that there are more as yet unobserved fundamental particles and unstable elements. So from the standard model, I mean, you think once some understanding was arrived at about the structure of atoms, then people started to say, gee, beyond the stable elements we know, there ought to be more, maybe very, very unstable and short-lived possible elements, and how we could go about even trying to look for them or construct them, make them in the laboratory. So there was a bunch of time filling in the blanks in Mendeleev's periodic table, where you said, gosh, I have reason to believe there are elements of this such and such and such properties that haven't been found yet. So the grounds for believing in them were there before there was direct observational evidence. In string theory, there's a postulate that there are more space-time dimensions than we thought there were, because we think there are only 4. In everyday life, it looks like there are 4. And in order for string theory to get off the ground, it turns out you need more than that. Originally, they thought 26, and then 11, and then 10. I don't know, they keep changing their minds, but more than 4 anyway. And in addition, in string theory, one of the main points is to postulate, and not just string theory, but other theories, so-called supersymmetric theories, postulate an entire set of particles that we've never seen any of these supersymmetric partners, photinos and gluinos and this and that, right? So those are things that some physicists think you ought to at least think are plausible, take seriously enough to design big experiments to look for them. So why? Right? Why should we believe in this multiplicity? Well, again, you'll see a whole bunch of different considerations, more or less direct observation, right? Galileo takes his telescope, turns it to the sky, notices that the apparent size of the planets is increased by looking through the telescope. You can now resolve the disks better, but when you look at the stars, they don't seem to magnify at all, and that suggests to him that they must be really, really, really far away, and so far away that you can start to imagine that they're actually in themselves as big as the sun, and the only reason they look point-like is their distance. You have that up once you accept that there are a whole bunch of stars. If you're a Copernican, then you naturally assume, gee, we've got planets orbiting our star. You know, nobody would have called the sun a star before that. We've got planets orbiting our star. There might be planets around all those others. So then with Bruno, you're going to say, I guess there are lots and lots and lots and lots of planets. And then Bruno thinks, well, maybe they're inhabited and maybe there are other civilizations and so on. Sometimes you've got implications of a theory that you've accepted for other reasons, like these unstable super heavy elements. People believed in them, and as it were, finally isolating them or creating them in the lab was, you know, reasons to break out the champagne, but was not a revolution, a scientific revolution, as Kuhn would say, because they were already anticipated. Why? Because you'd already accepted a theory that implied they ought to exist. That's more or less the way that the Everett people are going to argue you ought to believe in many worlds in quantum mechanics, because it's just an implication on their understanding, and it's an implication of standard quantum mechanics, and also an implication that you can't directly see them. Sometimes there's a kind of theoretical necessity or explanatory power. As I say, if you're going to do string theory, you got to add dimensions to space-time. So there you are. You know, if you've made the decision to go that direction, you're committing yourself already to more than is obvious. And then I guess that's all I got. Okay, so in the case of the sun-like stars, and I'm just going into detail about something I just said, from antiquity, people knew there were lots and lots of stars, but plain eyesight doesn't suggest that you should think of them as like the sun. As I said, the lack of magnification under the telescope suggested to Galileo, and also, of course, he used a telescope to look at the Milky Way and noticed that it was made of many, many, many stars, which was not obvious. Yeah, as I said, you couple that with Copernicanism, you get many planets and maybe many inhabited planets. And then, you know, you can get into theological problems because it's not clear that Jesus could save the people who live on other planets. All right, so there are all kinds of complications that get up. And once you have these many, many, many planets, that's more or less a necessary condition for believing that life emerged more or less by accident, by an unguided or non-teleological process. And so we have two questions here, right? How did life emerge from a lifeless environment? And then how did all the species we see emerge from the earliest forms of life? The second problem is handled by evolution. The first problem, nobody has a very widely accepted account of what are the conditions under which living, self-replicating organisms could evolve or could emerge. Evolve isn't really the right word, could emerge out of a non-living background. But it does seem for the main point, which is generally accepted, which is that we want an account of the emergence of biological forms that appear designed, but that there is no designer, right? There is no teleology. It's not aimed at anything, and there's no guiding hand that's doing it. It's more or less by chance. It's important. It's not more than important. It's absolutely essential if you want to hold that there be lots and lots and lots and lots and lots and lots of planets, because it looks like the emergence of this on any particular planet is going to be extremely unlikely. And so this gives us a really important model for one of the grounds you could have for believing in a huge multiplicity. And that's going to be relevant to the fine-tuning thing, which is what I'm going to come to. So you started with already Bruno assuming there were many, many, many planets, but then as time went on, you got better and better empirical evidence for them. You got higher powered telescopes, and then originally you could just see these stars wobble a little bit, which indicated that there was something orbiting them. And then eventually, as they got, and again, it wasn't a surprise. People kind of expected it. It wasn't clear how many planets of what size and so on you should expect to see around other stars. But given the huge number of stars, it wasn't that important how many average planets per star. You just needed to think there were enough planets that no matter how unlikely it might be that life would emerge, there were enough planets on which it could emerge that it would become plausible that it would emerge. And from that, you then get an explanation of these bioforms. Now, what's the logic of the explanation? Again, I take it this is clear, but this is where the central point comes in for some of these arguments for multiplicity of universes. Is you've got, first of all, you invoke what's called the weak anthropic principle, or you might call the weak bioform principle, or you might call the weak observer principle. That plays a central role in the explanation. I think what needs to be pointed out is that these principles come at no theoretical cost at all, because they're what philosophers call analytic truths. They don't, right? They must be true. They're necessary truths, which makes them costless. It also means that they can't do a certain kind of work for you. So what are these weak principles? The weak anthropic principle just says people will come to exist only in environments where they can. Right? Yes. Biological forms, call that the weak bioform theory. Biological forms will come to exist only in environments where they can. Observers will come to exist only in environments where they can. So nobody can complain about that. That's obviously true. Therefore, why is that useful to point out? If, and this is the big if in fact there are such things, they will be located in places, no matter how rare those places are, where they can exist. Now, we already know that bioforms are very rare in the universe, taken in an obvious sense. So overwhelmingly, most of the observable universe is interstellar space, and there's no life there. It would be a really serious logical error to say, gosh, how lucky we are that we as living things happen to find ourselves in this tiny little pocket that's not part of interstellar space. Because of course, there's nothing in interstellar space alive there, including us, because nothing can live there and nothing could emerge there. So that's, kind of a triviality. So the weak principles, because they're analytic, are free and they're uncontroversial, but they're also in a certain way powerless by themselves to explain anything. What they fail to explain or make a plausible or expectable is that these things will exist at all, because they're conditional claims. They say if they exist, then blah, blah, blah. But that alone gives you no reason to believe that they will exist or do exist. Now, how do you fill in that extra gap? Well, you could have a teleological kind of cause. You could say, well, something wants them to exist or made them to exist or designed the universe in order that they exist or something like that. I personally have no truck with that. I don't believe in any such principle. So if we don't have a guiding teleological principle, then the most obvious explanatory principle is that they emerge by blind chance, coupled with sufficiently many opportunities, right? If you're going to do something by chance, then you probably have to try a whole lot of times. And now the point is, again, quite straightforward, that if the number of opportunities for this chance process overmatches the unlikeliness at each opportunity, then you're going to say at the end, it can actually be both predictable and explainable why these things exist at all, and then trivial that where they exist is exactly in those places where they can. Now, the weak anthropic principle, again, I say, is completely uncontroversial, tautological, trivial analytic. It sometimes gets mixed up with this thing that's been called the strong anthropic principle, which is exactly postulating some additional piece of ontology, some additional thing that requires these things to exist, or ensures that they exist, or designs things so they exist, or something like that. And that has been generally rejected, I think, for good reasons, as being kind of both mystical and teleological. One of the advances of science has been generally thought to be the elimination of teleology as a fundamental principle. Things' existence is explained by appeal to the past of them and not to their future. This is why, by the way, retrocausation ought to be considered extremely controversial, because it somehow says, no, what's going on now is partially to be explained by appeal to the future and not to the past, physically. And that is to reverse what generally is thought to be progress. Now, so what this then gives rise to, because this is the form of the explanation, right? This happened by chance. Yes, the probabilities are very small, but there are so many opportunities for it to happen that despite the low probability in an individual case, it becomes highly likely it would happen at least once. That's an explanation for this, and you need the multiplicity for the explanation. So then you can have reasons to believe in the multiplicity that come from what we call inference to the best explanation. So this is a bit of science fiction, but we know if there is a sufficiently large cosmological constant and the universe, as it were, is expanding, that all the galaxies are receding from each other, and eventually they'll recede so far that each galaxy kind of loses contact with all the other galaxies, and the night sky, you'll just see the stars in your own galaxy, but other than that, there won't be any more. That could eventually happen. We don't know if it will, but I think if creatures arose in such a galaxy, as an observationally isolated galaxy, and they did some research and said, gee, it looks kind of unlikely that life would emerge if there were only as many planets for it to try on as there are in our galaxy. I think they would have reason to think, gee, there probably are more galaxies out there, ones we can't see. And if they knew about the expansion, they might say, gee, maybe they've just been pushed out of our visible horizon. And their grounds for believing in those unobservable things would be, well, they form part of an explanation of what we do see, which is that we exist. And so I think this is, inference. Now, that would be a pretty good principle on the basis of which they could come to plausibly believe that there are a lot more galaxies than they're able to immediately verify by any observational means. Now, you need to add here immediately that this principle, inference to the best explanation, is a really tricky principle to deploy. It's not obvious exactly when you're justified in appealing to it. And again, this is the kind of thing that philosophers will worry a lot about. but physicists in their everyday work don't. They're not trained to, and they're, but it's relevant. So my claim is it's a good methodological principle appropriately deployed. It tells us to prefer, at least to some degree, theories, a theory. If I have a bunch of theories and I say, but this one provides a better explanation of some phenomenon, then that's some reason to believe it's correct. But you need to restrict it. And this is not something that's, I think, widely discussed in physics, because there's some phenomena that just have no explanation, and you'd be wrong to look for one. There are some phenomena where the right attitude is to leave them unexplained, and therefore not to just grasp at some theory that does explain them because it's the best explanation you can find. One of your options is to say, this is just doesn't deserve an explanation. So let me give you a simple example. And these things are things that we normally call matters of mere chance or coincidence. Okay. In a certain sense, a matter of chance or a matter of coincidence has no explanation. So take my individual existence, right? Not the existence of living things generally or humans generally or observers, but me, right? It's really, 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 really unlikely that I should exist. You just trace back all of the kind of random sort of things, coincidences, my parents meeting each other. I mean, all kinds of, if it had rained on a different day, everybody's movements would have been joggled a little bit. I mean, this is chaos theory talks about the very precise dependency of certain phenomena on exact initial conditions. And you change the initial conditions the tiniest amount, and some things will still happen. Some kind of generically describable things will still happen, but most particular things, like my particular existence, won't happen. So what should my attitude be? Well, I could say, I need an explanation for why I exist, right? I need the Maudlinocentric explanation for this very important fact that I am an existent object. And so there must have been some guiding force that brought about all of these tiny little coincidences that led to but that's just crazy, right? I'm just here by chance, right? No reason I had to be here. No reason that my existence had to be likely or predictable or anything. It just was a matter of sheer chance. So that's an example of something else. So you don't want to say, one thing you do not want to say is, well, here's a theory that explains my personal existence, right? That I was written into some book as a central part of the development of human history, and therefore I had to, right? And no, right? There is just no explanation. I'm just a random kind of coincidental thing that happened to be thrown together. Okay. Here's another reason why IBE is a somewhat tricky principle, because you want to say, well, how do I know what the best explanation is? So here's an example. Here's something we've observed. There are these rotation curves of galaxies. That is, we can look at a galaxy, a distant spiral galaxy, and sort of figure out how fast the stars are rotating around the galactic center. And these rotation curves are not what you would expect if the matter generally in the galaxy was visible stars, and according to the general theory of relativity, or to Newtonian gravity for that matter. So those rotation curves are somehow evidence of something. But what are they evidence for? What's the best explanation of the rotation curves? Here, now it becomes very controversial, right? Some cosmologists look at that and say, that's evidence that there's dark matter, because the rotation isn't what you'd expect using the general theory of relativity if all the matter were visible, or if most of the matter were visible. And so they say, gee, notice you're using inference to the best explanation there. You're not saying I can see the dark matter. You're saying, I'm going to postulate the dark matter to explain what I can see. On the other hand, there are other cosmologists who say, no, 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 no. I'm just going to get rid of the general theory of relativity, right? Something has to give. But I'm not going to keep the general relativity and add this new matter to fix things up. I'm going to say we need to adjust the general theory of relativity, and then you have modified Newtonian dynamics. That explanation doesn't require dark matter. So clearly, the issue here is going to be arguments about which of these explain. First of all, the argument each one has to make individually is that it would explain the rotation curves. And then there's going to be further arguments about which one counts as the better explanation and why. So this is absolutely central to all kinds of questions. Good. So as I said, now I'm coming sort of to the main thing, but it should be obvious. If we thought there had only been one planet in the history of the universe, the standard explanation of evolution and the beginning of life is happening more or less by chance would no longer be plausible. We'd have to give it up. We'd have to find something else if there had only been one shot at it. So if you want to say there have to be, if you're going to have this kind of chancy part of it, there have to be many, many, many opportunities. And what else? It's just not many opportunities alone. There has to be a mechanism for sampling randomly in the space of the relevant space of possibilities. And we need then the weak principle to account for why it is we observe what we observe, because out of these many, many possibilities, only some of them will be where life could emerge, where observers could emerge, and therefore observers will certainly find themselves in that tiny, 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 possibly little subset. And therefore, if we judge that something needs explanation, and we judge that somehow it's in an individual case, it would be of extremely low probability, then that is grounds to postulate a multiplicity to complete the explanation. So that's where we're getting now to multiple worlds. There's obviously stronger grounds you could have for believing in multiple worlds. You could have more direct observational evidence. You could have directly see them. You could see other consequences of them. That would be great. I'm not saying that inference to the best explanation is the only kind of evidence you can have, but it's certainly important evidence, and you need to think hard about how to deploy that principle. Obviously, you know, we have reasons for believing in a huge multiplicity of planets that goes beyond, we need a huge multiplicity of planets to make the theory of evolution work. We have direct evidence. We've gotten better and better evidence. We have evidence of many species and so on. And you could have a theory that just implies their existence, like eternal inflation or a cyclic cosmology. That's some grounds for believing in a multiplicity. That also doesn't have to be directly observational. You have reasons to believe some theory, and the theory itself implies it. Now, where does that bring us with respect to fine-tuning? Notice, if you're going to use the multiplicity together with chance to explain something, you need for that multiplicity to sample in the class of what of possibilities. And as one of the things we're worried about is this so-called fine-tuning of the what we laughingly call the constants of nature, that the mass of the electron and the charge of the electron and the mass of the various quarks and so on fall in very, very narrow ranges, which would allow for the development of complex structure. And more than just complex structure, sort of relatively, a lot of complex systems with different structures that are relatively stable, so they could interact and you could have evolution and things like that. The kind of multiplicity you need to explain that is a multiplicity of sampling among these different possible sets of constants. That's why I'm not going to talk here about many worlds, because the Everett interpretation of quantum mechanics, as far as I know, contains no such mechanism. It gives you a multiplicity. It does not give you a multiplicity of these constants. So, you know, just put it off the table as far as this particular problem goes. we obviously have to regard these things we call constants as not really constant, right? They have to take on different values in different places. The one thing that's sort of given us a picture, which I understand only in the most, gross kind of popular way. I'm not an expert on string theory, but at least it gives you a model of how you might do this. Goes something like this. It says, well, yeah, the constants aren't really constant. They're determined by the geometry of a particular Calabi-Yau space where you have all these extra, now we're back. We need more dimensions. We're going to add dimensions of space-time. We only see 4 of them because the other ones compactify. And as a matter of geometry, they can compactify in many, many, many different ways. And somehow the values of these constants is a function of how they compactify. And those values of these so-called constants, as these compactify in different ways, sample across the space of possible constants in a pretty uniform way. I mean, it has to sample all around because the idea is that there's only a very tiny sweet spot in that space of parameters, which will lead to stable complexity. And then you need a mechanism by which you do this sampling, which I guess is supposed to be internal inflation and this, formation of bubbles, by which many, many, many such compactifications occur in a more or less random way, whatever that means. Now, I can't fill in the details of these steps because I don't understand string theory well enough. I'm not sure anybody does, but those are the steps you would need to fill in to understand how this could deal with the fine-tuning problem. So I'm at now my last slides. As far as string theory goes, I'm not a fan of string theory. I've never been a fan of string theory. I'm not here advocating string theory. We seem to be getting more and more empirical evidence it's not correct. But I do think that if all of those steps that I just laid out can be filled in coherently, that it would provide an adequate explanation of why the constants of nature around here, the ones we see, the ones in our bubble, lie in this apparently very small region of parameter space that would support complexity, right? And that fact, unlike the fact that I personally exist, which I think requires no explanation, it's just a matter of chance, right? I happen to exist. I think the fact that the universe supports that kind of complexity doesn't seem to me to be the kind of thing I want to just wave my hand at and say, oh, that's just a matter of chance, right? So I think this is the kind of fact we would want an explanation of and not to write it off. And therefore, I think that by itself provides some grounds to take that theory seriously, as much as I don't like it for other reasons. And I think any other theory that could give you this kind of mechanism for sampling among these various possibilities, which is going to mean it's going to be a many universes theory because there are going to at least be different regions with these different apparent constants. And most of those regions will look nothing like the one we see. I think that's reason to take those things seriously because they would fill in that explanatory lacuna. Good. So I think there is a good scientific motivation to seek out these kinds of theories and that they'd be more plausible than alternative theories, ceteris paribus, right? All things being equal in terms of their reason to believe them, if one of them could solve this problem and the other one couldn't, you'd really have good reason to believe the one that can. But having said that, of course, the cetera are never really exactly parity. You're never confronted with two theories that are exactly the same evidentially, except for this one thing, right? So you have to take into account the full range of evidential considerations. Now, there is a caveat I want to make, because you might think on saying this, what I'm saying is, gee, you should just look for theories with lots of multiplicity, because they can do this explanatory job. But you really have to notice that's not true, because you can have too much multiplicity. You can go too far. I think Max Tegmark went too far with his level 4, which basically says that every mathematically possible structure corresponds to some physical reality. Tegmark himself would say corresponds is the wrong word there, that every mathematical structure is a physical reality. I think that's just kind of, well, that's implausible. But anyway, let's just talk about corresponding. What would be the problem of saying for every possible mathematical structure, there's a physical reality that corresponds to it? Well, there'd be too many of them. For example, there's certainly a mathematical way to describe a physical universe that looks just like ours up until now and then goes kaflooey and falls apart in any number of an infinite number of different ways, right? Blows up, disappears, dissipates, whatever. I mean, there's a lot more ways to describe chaos than there is to describe regularity. And so if there were that many physical things, you could say that could account for our existence up until now, but it would kind of predict at every moment that we're about to end our existence, right? It would say, well, some small number of these will keep going in a coherent way, but most of them are about to fall apart. And so what we do here is we apply this notion of typicality. So where we have a huge multiplicity, we look for typical characteristics that in some sense most of these things have. And for example, typical real numbers are irrational. Typical integers greater than 10 to 100, they're composite and not prime. And among, I would say, if you've got all the mathematical possibilities, typically they don't have any describable generic kind of macro scale regularities at all. There are just many more ways that things can be chaotic than non-chaotic. And so when in physics, you often appeal to typicality to explain what you see. If your multiplicity gets too large, you're going to change what's typical. And therefore it can reduce the ability of the theory to explain. So it's not that there's a pressure always for more stuff. It has to be of the right kind. And so this is what Maxwell and Boltzmann did. They showed that evolution in a dilute gas to a certain velocity distribution would be typical. Doesn't happen in all cases. Mathematically, you can describe cases where it wouldn't happen, but overwhelmingly most of the initial conditions will lead to this kind of result. This is what they showed. Similarly, arguments that a system in a low entropy state will typically evolve to a higher entropy state. These are good scientific explanations. You have to now think about what typicality means. In these cases, it's tied to statistical independence, but this is not the place to go into what would be an entirely new talk about the concept of typicality. But in the history of science, this is often used. And that's not in tension with appeal to the weak principle. So you say, look, being habitable is highly atypical among planets. Most planets are not habitable. But among the habitable planets, large bodies of water will be typical. And therefore, we shouldn't be surprised that we find ourselves on a planet with large bodies of water, even if they're very rare, even if they're very rare in the universe. The important thing about this is this gives us another empirical test where you can make a typicality argument. You're going to argue what you see ought to be typical. And so you can make predictions given what? There has to be enough multiplicity to make it likely that observers will exist. Among the instances where there are observers, if some features are typical, then we can ask whether what we observe is typical according to this theory. And if it is, then I think that's good evidence in favor of the theory, right? That's an evidential test a theory could fail. I think in Tegmark's case, it fails, right? Tegmark really should predict that the world at any given moment that we're in is about to fall apart. And Feynman made similar comments about certain explanations of the second law of thermodynamics, that what they would predict is that if you looked in a region of the sky where you haven't looked yet, you won't see any stars, because that's what would be typical on a certain understanding of how we got to the present state we're in. So what do we need? We need the right kind of multiplicity as a component of an explanation for apparent fine-tuning without teleology or without appeal, I think, to any strong principle. I think that's reason to seek out the theories, but they must have a mechanism for the variation, a mechanism for production of enough multiplicity, and a principled notion of typicality to appeal to. And if we get that, then we have various reasons to take such a proposal seriously, including maybe we could directly observe some of the multiplicity. Maybe we could directly observe causal consequences of the multiplicity. Maybe we have other reasons to believe the theory that implies the multiplicity, but among the reasons, and one I think would take seriously, is just that it would account for would resolve the fine-tuning problem, and that other theories without the multiplicity couldn't resolve. So that's where I think we are with respect to why take some of these multiplicities, theories with these multiplicities, many worlds, as serious, under serious consideration. Okay, so that's the end of that story.
Great. Well, thank you so much, Tim, for your presentation. It was really fantastic, and thank you for introducing some pure philosophy of science, questions that have been going on for many years, since Vienna Circle, if not earlier. So thank you for bringing these forwards. So just before we open it up to discussion to everyone, after 2 sessions of absence, we welcome back Shantena, Director of the Prairie Center and Chair of this event, to see if he's got any questions or comments.
Thank you, James, and thank you, everybody. Thank you, Tim, for a very rich and challenging exposition. I'll take advantage of the privilege I have of speaking now to ask a question. And I'd like to propose you the following question or idea. I'm starting from what you described as the many Ekis. What we thought as a singular isolated case turned out to be general and vast. So I'm referring to an idea which was introduced by Murray Gell-Mann, who was the teacher of Jim Hartle, who was my teacher. He noticed that one way in which physics progresses is by jettisoning extra luggage, by getting rid of notions that were considered like general and universally valid, and were eventually discovered to be secondary and particular, like, let's say, the Earth at the center of the universe, which eventually is just like a perspectival factor of where we're through which we're looking from. So I would like to have your comments on the idea of like the movement from what's perceived as general and then realizing that that's particular or perspectival. Whether that, how would you include that in your description?
Well, I think what you mentioned in that particular case is actually an example that I talked about, right? Which is that we went from thinking the Earth was unique to understanding that it was one among an untold number of planets. Now, the perspectival part, some of it is like the anthropic principle. It's just analytically true. What observers will observe will be regions where observers can exist. That nobody can dispute that. And therefore, naively believing that what you see around you must be typical. I mean, this brings us back to typicality. Naively believing, for example, that what you see around you must be typical, that's a terrible mistake, because the region we happen to be able to observe was not randomly chosen from all possible regions. A randomly chosen region just in the observable universe would be somewhere in interstellar space, intergalactic space, and would be pretty empty. So sure, you're going to make, I mean, it's a fairly obvious error to think that what you see just when you open your eyes can be treated as if it were a random sampling from what there is, for these sorts of reasons. And so you make progress that way. I'm not sure if you see that principle as in tension with anything I said. I don't see any conceptual tension at all.
Thank you, Tim. Yeah.
Thank you, Shantina, for coming in. So yes, now we can open it up to everyone. I can see some people already have their hands up, but just as a reminder, you can use the raise your hand function, which can be found under reactions at the bottom of your screen. Physically raise your hand or write your question in the chat for me to read it out for you. So firstly, we will go to Bernard, as I believe he has some comments.
Tim, first of all, I must say I'm sorry that you had to revise your talk because of the overlap with what I said in my talk, but I can only say that from my point of view, I'm really pleased because what you said was really interesting. And also, I have to say, I'm delighted that I find that I sort of have a very similar perspective to the multiverse and the anthropic tunings as you. I mean, I don't agree with all philosophers on this matter, so that was a delight. In particular, for example, I agree with you about the Tegmark level 4, but I had not used the argument before. You used the typicality argument. I thought that was a really nice argument for sort of, if you like, demolishing that perspective. I'd make one semantic point, which is to do with the term strong anthropic principle. You use the term strong anthropic principle in the sense that it required us to be here. And that was indeed the sense in which the term is used in, for example, Barrow and Tipler. However, when I did the paper with Martin Rees in '79, we used it in a different sense. We merely used the weak anthropic principle to say that we have to exist in particular places and times given the constants of physics. And we define the strong anthropic principle as merely saying that the constants themselves are fine-tuned. And that's different from the Barrow-Tipler definition. I mean, if you take the Barrow-Tipler definition, I completely agree with your conclusion. But of course, the point is that with our definition, the one with Martin, what we call the strong anthropic principle just becomes a manifestation of the weak anthropic principle if you believe in the multiverse. So really, that's just a comment to say that I agree with that, sort of also clarifying in case there was any confusion about what one means by the term strong anthropic principle. I think there's still semantic confusion about that because people use the term in different senses. Now, my question was going to relate to the first part of your talk, where you were talking about the fact that you can't make a clear distinction between science and philosophy, and that's something I agree with you as well. That and that's why I suppose I can justify working on the multiverse, for example, and I love your story, incidentally, about Bell, and how he did his work in the weekends, and that was really what was so important. But my question is this: despite the case you made that there's no clear division between physics and philosophy, or well, science and philosophy, the fact remains there is a big argument that goes on in the context of string theory and in the context of the multiverse as to whether it's science. So, for example, I've had many debates with George Ellis, where I argue that the multiverse is respectable science and he argues it's not. He argues it's philosophy. So it's not that he doesn't disbelieve in the multiverse, he just says that such speculations are not in the realm of science, they're in the realm of philosophy, which doesn't mean they're wrong, it just means it's not science. So I would just like to ask how you react to that, because at the end of the day, George clearly has put a barrier somewhere and said, well, we're on the multiverse is on the side of the philosophy, not science. So how would you react to the argument with George?
Well, yeah, I mean, look, I would be interesting to have that discussion with George. I think that it's a it's being used there as a funny kind of rhetorical cudgel. What I would want him to do is explain to me, because he's the one making the distinction, what exactly he has in mind. I mean, it seems to me the only relevant question, once you have a clear ontological proposal, and it can be whatever you like. It can include, theology. It could include panpsychism. I don't care. But state to me clearly what you're saying there is in the world. And then I'm going to ask, okay, why should I believe that? And that's this question in confirmation theory or evident, what is the evidence for it? Now, if in discussing that, I don't really see where a distinction, when you say that's not science, I take it what he might mean is, oh, there's no evidence for it, or there's no reason to take this seriously. That's the only thing I can think he could mean. If you ask, and I know because I've asked him, if you ask Ed Witten, why should I take string theory seriously? He'll say, because there's gravity. And, it automatically there drops out a massless spin 2 particle out of string theory, and gee, that's gravity. Now you can dispute that or whatever, go into the details, but it's an attempt to answer, why should I take this seriously, right? And in any case, everybody agrees that part of science, by anybody's definition, part of science is the development and exploration of novel hypotheses and novel theories. I mean, that's got to be part of science. Science isn't going to progress if there aren't people who are willing to try and rethink or reformulate or, change the foundations in various ways to see what happens. I don't understand how anyone could claim doing that per se is not science. Certainly the string theorists are doing that. I might say, look, I don't think the existence of gravity really counts as such a strong reason to believe string theory as Ed Witten wants to say it is. I mean, we can have a dispute about how powerful these grounds for taking something to be credible are. But just to have these two boxes and say, oh, here's science and here's philosophy, I don't see what you get out of that. I mean, it takes you away from the interesting discussion, which is, all right, let's get down to brass tacks and explain to me why you think you should take this seriously. The answer might be, I don't think you should yet, right? I think it's an interesting idea mathematically. I want to develop it. I want to see what happens. That's part of science too, right? Why get yourself in a box of saying that's not science?
Well, I like the way you use the word yet, because I think that really is crucial. Because, I mean, George's own answer would be that the multiverse is not science because you can't see the other universes, it's not falsifiable, and that the multiverse theorists can essentially predict anything you want, so it's not useful. But I mean, you've given some of the counter arguments, but I think perhaps the most crucial counter argument is that, first of all, from a sociological perspective, if science is what scientists do, there are a large fraction of very, very bright scientists who are spending time on this from a practical purpose. But also, I think the key point is that even if we don't have any empirical evidence at the moment, apart from the indirect evidence from fine-tuning, etc., the fact is that we may well, in another 20, 30, or even in another 100 years, we may have the empirical evidence. And right. So it may not be proper science yet, but it can be in a sort of intermediate state before it becomes proper science. And
well, this is also a point that Einstein made when he was responding to this kind of very crude positivism that said, oh, science is just taking the observations or the observation language or something, or statements in the observation language and, codifying them or boiling them down or something like that. And Einstein said, no, 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 it's the theory that tells you what can be observed. So you can't even make a statement, there can't be observational evidence of X until you've gone very deeply into the theory and probably understood it better than even the people developing it. Because, all kinds of things happen that people find out. Look at what you can do with quantum mechanics that people 50 years ago had no idea you could do with it. So it's not immediately obvious what the possible empirical consequences of a theory even are. Right, so you really shouldn't be dismissing anything out of hand on that.
If there was never any evidence, thousands of years in the future, would you still be happy to say it should be it's part of science?
Well, look, if the obvious thing to say about something of which there's no evidence is I have no reason to believe it. I mean, it's as if I'll tell you what this sounds like to me. Sometimes people get into a big debate: is X art? As if calling it art is a big deal. Lots of stuff I think is bad art. I'll say, okay, it's art, fine, but it's bad art. Just putting it in the box of art doesn't make it good. One of the things we want of our scientific theories of any theory is to have good reason to believe them. So if what you're telling me is if in 1,000 years there's no reason to believe string theory, then in 1,000 years there's no reason to believe string theory. What is putting it in or outside of a box called science add to that comment? I don't see that it adds anything.
Well, thank you. I asked too many questions, so I'll let the others come in. But thank you very much indeed, Tim.
Thanks. And thanks for clearing that up about the meaning of strong anthropic principle, because yes, I learned it from Barrow and Tipler. And so I never, but you should be aware of that because people can, make that mistake because of that.
Well, thank you, Bernard, anyway, for sparking this interesting discussion about science. We'll next go to Angelita. Oh, you're so muted.
How about now?
Hi, yes, we can hear you.
Very good. I said, hello, Tim. Good morning. It's morning here. I'm speaking to you from San Francisco, California. And this is the homeland of the Ohlone people and the guardians of this peninsula, So I think I wanted to introduce what is now becoming more and more common in the Americas, which is called land acknowledgement. So whenever we speak, we first are starting to acknowledge the land we're speaking from. And as I was listening to you, and I really appreciate being on this call, because I appreciate a scientist who's also a philosopher in the same breath. And as I was listening to you, I was thinking maybe another practice that we might consider is talking about modern scientists or modern science. In the Americas, we say, you Europeans have only been here 500 years, just 500 years. And our science has been going on for thousands of years. Our pyramids were built and our canals established. And there's a lot of evidence, I'll use the word that I'm interested in asking you about, that indicates that for millennia, we have been very productive and in harmony with this land that we're on. And so I guess, Bernard, I don't think we have 1,000 years to wonder whether string theory really works. I'm working on a 10-year plan myself that it seems both the elders and the ecological scientists are telling us that we need to change something or this earth that we're all on is going to react. So I'm listening to you this morning, Tim, thinking about all of that. So essentially I'm placing myself, before I ask my question, I had the great, wonderful joy of being in a salon with David Chalmers and Stuart Amaroff and 80-year-old mathematicians. And I was considered the Native American scientist, indigenous scientist. And we would all come together monthly to talk about the issues that the Perry Center is now bringing to us all. And the question I still remain with, of course, as is, I've had also the opportunity for many, many years studying the quandaries of quantum physics within the university. So I'm kind of have a foot in each world. So to you, as a scientific philosopher or philosopher scientist, I'm asking you about the measurement question, which is enormous and it is the limiting factor in our equation of understanding. But more specifically, I'm asking you to help me understand what is evidence. I mean, I sit in a place of holding wisdom and knowledge and empirical information that's been passed on in oral traditions and many things that would take forever to explain. And I wouldn't have the expectation that someone schooled only in an academy in a European setting would know what I'm talking about. So I'm not talking about that. My foot is squarely in the quandaries of physics in modernity. What would somebody consider evidence if I were to try to speak to them about what I know? And I'm asking that as a friend, as someone who knows that there are so many good-hearted scientists that are aware of the limitations that modern science is running into. And so many scientists who are aware that we need to establish new patterns of communication. And as I've been working with Perry, the Perry Center, and working with other universities and such over the last year in the pandemic, I'm running into evidence. What we consider evidence, I think, is one of the major obstacles to us being able to understand each other and work together. So please, whatever you can think of, or if I took too much time, John, I'm sorry, as Native Americans ask questions for 20 minutes, that's how we do it. We have a lot of backstory to inform people before we actually ask what we're interested in. So if I've taken my time, I'll give James my email and you can refer me to someone who can help me understand evidence. What is plausible evidence to a modern scientist as it relates to the native scientist and the knowledge that we carry to work together? This is a very, thank you.
Yeah, let me just make a few comments to situate the way I would think about this. In terms of the native cultures anywhere, there are certain things anyone should think they've worked out that would not be obvious to a newcomer, right? Because you have generations of practical application in terms of cultivating things, in terms of understanding the species, in terms of there are lots of things that there's an obvious good reason to believe that they would know better, have certain information that would be more reliable than someone who just stumbled into that area. On the other hand, there's no reason to think that any culture anywhere had any magical knowledge. My understanding of this is that some native peoples here kind of farmed their, destroyed their agriculture by over farming it or not properly looking after the land. What else could you expect? I mean, no, that's just to say they were people like any people. And, if you have something that works in the short term, you may not appreciate that in the long term, it could have deleterious consequences. So I don't want to be, too romantic about it. I think that over time, things that work and are sustainable will become kind of part of the lore. But we all know there's also parts of any lore that's handed down, oral traditions that are, just myths and other things that would not be of so much scientific interest. As far as evidence goes, you see, it's interesting about the word evidence that it comes from the word evident. The evidence is stuff that there should be no dispute about. And the difficulty sometimes is pulling back far enough to get to a description that everybody agrees about. So for example, in quantum mechanics, because you were sort of going in that direction, that in a two-slit experiment, you get a certain pattern that builds up on the screen, that you get dots that occur individually, but build up to a kind of interference pattern. That's evident. That's something that nobody is going to dispute. And the beauty of that is it gives you a platform from which then to have a discussion. At that point in quantum mechanics, the discussion is, okay, but what accounts for that? Is that because individual particles are coming and hitting the screen or something else is happening? And as you know, there are many different ways to try to account for it. And then you have to go into each proposal and analyze it individually and see, have you filled in all the gaps, or does this really explain it? And I think at least there's a lot of discussion that people even on opposite sides can have and at least communicate with each other in trying to fill in those gaps and just lay out as explicitly as possible, here's what we agree on, here's what I infer from it, or here's how I explain it, here's what you infer from it, here's how you explain it. That gives everybody a space to, you know, explain themselves, and then hopefully where there's disagreement, you can see if there's some way to make progress on.
Okay. Well, thank you, Angelita, for coming in. And unless you've got a follow up.
Just a little tiny one. So what you've just said to me reinforces and reifies this direction that I'm going on, which is that perhaps we don't need more information. We really don't need new information. What we need is to come together in what it means. Because over the next 10 years, what really is important is what we know so far. What does it mean to us? And what does it mean to our future?
Certainly for, I mean, both in the sense of, say, quantum mechanics, the main phenomena that I still talk about today have been known for a century, nearly a century. It's not new phenomena, typically. Certainly in the case of climate science and the really pressing issues in front of us, we have the data and we have it's not hypothetical. We have observations. We have all, you know, it's a different issue. What's motivating people who want to deny that we're in a crisis situation. And you're right. I mean, that is going to take something more than just doing another study or something like that. Yeah.
Well, thank you, Angelita, anyway, for coming in and raising these issues. Next, I would like to ask a question that comes from the chat, which goes, what do you think of the statement, nothing has meaning, but the meaning that you assign to it? And it'd be interesting to hear your thoughts also in the context of science, how science is conducted.
Well, I mean, the word meaning is a very polysemous word. I mean, meaning means many different things. If what is meant here is something like deep significance, right, importance, I guess in many cases, of course, I disagree. I think, for example, I think there are moral truths, and there are truths that exist independently of whether we acknowledge them or even aware of them. And therefore, the significance, say, of certain horrible immoral practices is there whether or not we acknowledge them. And our, you know, refusing to acknowledge them wouldn't make them go away. So I would be a bit worried about getting too subjective about that. Certainly in physics, and this was, you know, Bell's main complaint about quantum mechanics was that it was, as he said, professionally unclear. It involved terms like measurement in the foundations that he said shouldn't be there, or macroscopic, microscopic. In his essay against, quote, measurement, his main complaint is that some accounts of quantum mechanics have sitting in their foundational principles fundamentally vague and unclear concepts, and you want them to be sharp and mathematically formulable and so on. And so I don't think that's subjective. I think that's a real, honest, clear technical requirement that has failed to be met, and that physics will make progress if quite honestly, if physicists hold themselves to a higher standard of clarity of what they mean when they say various things.
So just as a quick follow-up, are you saying, or in your opinion, does science give the same importance or significance to all valid observations? Because of course there are observations which aren't scientific.
Well,
or
I'm not sure in what sense. I mean, observations, when you say an observation, you usually mean a report of something that one would normally think a normally well-functioning person who's not under the influence of drugs can reliably report, right? That you can take the reports with a high degree of confidence that they're just accurate. And those you should take from anybody unless you have some reason to believe that they're either intentionally trying to deceive you or they were under some, of course you should take them seriously. The point of science is to try and account for such things, is to come up with theories that will explain, will put what we observe into a comprehensible larger framework. So yeah, I mean, you would have to go into particular cases. I don't think there's much that can be said at a very high level of abstraction on the question you just asked. I would have to know what particular issues someone had in mind that was motivating that question.
okay, great. Well, thank you for answering. And that question came from Med. So yeah, so next we will go to Gary.
So let me ask this question. As a philosopher, let me pose the possibility that in the 17th century, we took a left when we should have taken a right. And that we ended up becoming Cartesian nominalists when we should have become scholastic realists. And that what we're stuck with in nominalism is kind of getting lost in the multiplicity, when in fact it's the categories and the universals that are real, not what is apparent in front of us, right? Because in fact, if we look at what is the implication of nominalism, it is that there are individuals who are separated. There is no true communication that's occurring. Whereas if communication is the reality, then that means that this idea of signification and meaning is where reality lies, and that we're stuck in this kind of mode of physicality and thingness that is leading us in the wrong direction, and possibly leading us, I mean, going back to Angelita's, into extinction within the next short period of time. I'm just wondering, I mean, I'm very much in favor of, for example, what Peirce was telling us, Charles Sanders Peirce was telling us about the threat of nominalism, the threat of becoming too engaged by individuals and by our immediate physical reality, and losing track of what is underlying that at a relational level. And I would say that, you could view evolution itself as a process of semiosis that selects for those entities which are able to communicate effectively with each other. And that's a principle, right? I mean, that's a principle that's been put forward by a biosemiotician, Jesper Hoffmeyer, which is the principle of semiotic freedom, that as a driving principle in evolution, which is basically why we're here, because we're language creatures, right? So we're able to actually communicate effectively with each other and form communities around purposes that allow us to actually achieve things that we individually could never have accomplished. Do you follow what I'm saying? Like,
yeah, I understand. Let me because you ran up and down a whole scale of issues there. So let me try and separate them and make a comment. One is this idea about categories of being, right? What kind of things are there? The reason why I put quantum state with a question mark in the category, as it were, in the heading individual structure law, is that when you get into quantum mechanics, just if you're doing fundamental physics, you need this thing we can call a quantum state. It has some kind of physical reality. I think it's an unfamiliar thing. I don't think, you know, if you ask, oh, which Aristotelian category or which Cartesian category or which, you know, Aquinian category does it come under? My answer is, what makes you think any of those people would have a good category for it? I mean, you don't, you know, this is a novel kind of thing. I like to just say it has its own category, quantum state. Let's try and understand it. It obviously is a kind of holistic sort of thing. And so, runs against a certain kind of Democritean picture of these atoms that are just, you know, whacking into each other. But on the other hand, I should say, I think people like to use concepts from fundamental physics as sort of metaphors, which is a dangerous thing to do. I mean, I had a dear friend of mine was Renee Weber, and she was kind of a mystic and then got into quantum mechanics. And she would also say, oh, you know, the holism and the interconnectedness in quantum mechanics is telling us that we should all cooperate and so on. And I said to her once, I said, Renee, so you mean you're telling me that if you know, Newton had turned out to be right, we should just kill each other? And she said, no, I don't think that. And of course she doesn't think that, right? I mean, fundamental physics is not instructive to us in questions like how should we form communities and how should we respond to climate change and how much should we be attacking each other and how open should, you know, these are questions that are going to get the right answers quite independently of what fundamental physics looks like. And so there is a tendency to kind of think, oh, I find this thing in fundamental physics that I can serve as a metaphor for a moral point, or even at the level of what you're calling communication, right? I don't think there's a certain sense of communications in which I don't think, you know, atoms communicate with each other. They influence each other. They're jointly, you know, and my, you know, my worry about that is that if you took the metaphors too seriously, you might find that a new discovery in physics would undercut your entire ethics, and you don't want that to happen, right? So, you know, I would prefer to keep those issues rather separate because I think they are.
Well, you made an argument for continuity in the beginning, and I would say that, yes, there is a continuity. There's a continuity between physics, metaphysics, and ethics and morality. You cannot separate them. And in fact, what physics is telling us, what quantum physics is telling us, is that you cannot put partitions into the universe. You cannot separate pieces of the universe into different parts. Right? Because ultimately it's all interconnected and it all influences each other, right? I mean, the Newtonian mechanics only works at a specific scale because the interactive component is negligible. But when you actually, what quantum physics is telling us is that Newtonian mechanics is an illusion. I mean, it's not the reality. It's perhaps what you might call your actuality at those scales, your physical actuality.
Right.
That is not the underlying reality.
Look, I agree with that, but you know, Newtonian physics will get you to the moon and get you to Mars, and the level at which we need to do things to say stop the climate catastrophe, I don't think depend on quantum mechanical considerations. More or less, I think
they depend on moral considerations.
More or less 19th century physics would be enough.
Great. Well, thank you, Gary, for coming in and contributing. We'll next go to Paul.
Okay, yeah. Hello, Tim.
Hi, Paul.
Look, just a very quick question, because people might be a bit confused with the conflict between what your talk and mine. I mean, most of the time you've been talking about multiverse in the context, well, in the context of the cosmological multiverse. And I know, you're pretty dismissive of the many worlds interpretation, but look, I think you said something like the idea that quantum mechanics gives us a reason to believe in splitting or that sort of thing. That you don't think that's right, but would you agree that before the many worlds idea is even a candidate for being an interpretation of quantum mechanics, it's got to be seen to be intelligible, and you don't really believe that it's even intelligible, and you've got good reasons, I think. I mean, I think you've got reasons which have not been given enough consideration, but would you say that really your first objection to the Everettian view is that it simply is not intelligible?
Well, I don't, if someone says, here's a theory, there's one fundamental thing in the world called a quantum state. Here's a space of all possible quantum states, or at least representatives. That's a complex vector space. Here's a dynamical law, Schrodinger's equation, or something like that. I can comprehend that, right? It's not that I don't understand what you're saying. If that's all you tell me, and furthermore, this one thing you tell me only exists in an unbelievably high dimensional space, as it were, I'm not going to understand straightforwardly how to relate that to the world I think I'm aware of opening my eyes, right? The world I think I'm aware of opening my eyes has a bunch of fairly localized objects that are displayed in a three-dimensional space. So, I mean, the first thing is that, as Bell would say, the theory doesn't have a set of what he called local beables. And,
Sure.
and it's via the local beables that I make the connection to my experience. I wouldn't say I don't understand the theory. I don't understand how it's being proposed as a theory of the physical world we live in for that reason. I mean, that's one main issue that I think has not been addressed sufficiently in the literature.
Oh, yeah, okay, look, sure, I understand that. I mean, that's the sort of ontological, metaphysical question, which I really didn't touch on in my talk. It came right at the very end. And I agree with you that the lack of hidden variables in many worlds creates a great problem. But just the idea that it's even credible that it could be a situation that we're splitting into futures which are more or less probable. It's that idea, the idea of splitting, and that probability can be a property of multiple futures. For you, that remains unintelligible, do you think?
I mean, unintelligible is such a strong word. I do think, and this was the point I was going to make. I said I had another little set of things about this. I mean, in your presentation, you talked about these branch weights and treating them as probabilities. Yeah. I mean, technically, the branch weights, what you normally call those, are actually complex numbers, and you have to take their absolute squares to get something that even has the right mathematical form to treat as a probability. And the question of why you should treat it as a probability, right? What is the justification of taking these things and squaring them and then acting as if they were probabilities? Yeah, I mean, I think everybody agrees. That's why Deutsch and Wallace and so on have gone on to these rather complicated decision theoretic arguments, which you didn't really go into, but that's where they've been driven to try and justify that. And I must say, at this point, I'm not convinced by any of those arguments for reasons, which would be too technical.
Which I'm aware of. But I mean, well, in my opinion, those arguments, if they're good, they're just justifications of the principle. I mean, I think they don't do what Wallace and co think that they do. But I mean, really, what I was trying to do in my presentation was, I mean, it's something rather new, but a thought experiment which could make this idea that there could be sort of branches and that they could probability their probability. Because yes, I mean, the weight, I mean, what I was calling the weight simply is, of course, the squared modulus of the amplitude. Yeah. So I mean, Okay.
Let me actually just make one real quick comment. I mean, this is going to be a little telegraphic, but you know, your pictures and your title about being dendritic gives you a geometry of this sort of main trunk with these things, rather distinct things coming off it. Yeah.
Right.
If you imagine a single radioactive particle sitting in the middle of a spherical set of detectors, with, as it were, the wave function continuously leaking off because there's no particular time. It's not clear that that structure, even in configuration space or whatever, looks exactly dendritic.
Well, I mean, I did.
It's kind of continuous, you know, it's kind of a continuous thing. It's there aren't these sudden branches that come off.
Well, I mean, yeah, absolutely. But I mean, I did sort of touch on that in the talk. The idea you've got this a radioactive particle, and it's a continuous process. Okay, on a time scale of 10 to the minus 20, etc. Then, in my opinion, if you were going to go the other direction, it has to be little threads coming off all the time. There are little branches coming off, 10 to the 23 per second, very thin branches coming off. It seems to me that that has to be the picture if you're going to take that sort of view seriously.
Yeah, I'm not sure the Schrodinger equation, as we understand it, gives you that picture.
Okay.
So if you think you need that picture, I think this is a point at which, I mean, Wallace himself says, look, I can't count branches. There's no actual fact about how many there are. Branch talk is vague talk. I mean, he's going the other direction. You're sort of suggesting there has to be more structure in there than I think you would get out of Schrodinger evolution. But anyway, this is a little bit,
fair enough.
A little bit shop talk right now.
Right. Well, thank you, Paul, anyway, for coming in and responding to the talk. So as we're just over the 2 hours, I guess we should start closing. Tim, do you have any last minute closing comments to finish this session?
Nope. I think I said what I wanted to say.
Cool. Perfect. Well, thank you so much, Tim, for joining us today. Thank you for accepting our invitation. Really was a fantastic session. It really made me think again about philosophy of science, which is, of course, something that not everyone touches on, but is very important. Thank you all for coming today. Thank you all for your questions and contributions and discussions. Hope to see you all next week, where we'll have Bernard Carr again, who will try to answer the question, is the multiverse in the mind, or is the mind in the multiverse? And this will be on Saturday, and then on Sunday we'll have our closing panel, where we will have the different speakers from the last few weeks who will be reflecting on the topics that have emerged. Of course, it will be taking questions from you all as well, so make sure you've got some questions ready to ask them. Finally, you can contact us for any problems or questions, either on Sutra or on our website, or social media, or by email us directly. James@percenter.com to contact me, or Eleanor@percenter.com to contact Eleanor. Thank you all again for joining us. Thank you so much, Tim, and we'll see you again soon here at the Power Center.
Thank you.